Thanks. Yeah, your pronunciation was right. Thank you. This is Ozlem Turker Bayrak from Cankaya University, Turkey, and my colleague is from Middle East Technical University, Aysen Akkaya. We deal with robust estimation of polynomial regression analysis under the long-tail symmetric distributions with a new estimation technique, adaptive modified maximum likelihood method. We know that in application, the relationship between the variables are non-linear, so this is why mostly polynomial regression is used in practice. And also we see that non-normality is a common feature, and therefore we need to develop some robust estimation methods for such modelings. However, the difficulty is that non-normality induces extra non-linearity into the likelihood equations so that maximum likelihood estimators cannot be derived analytically. They can only be solved numerically, which are problematic in case of data anomalies like outliers. For this purpose, different non-parametric regression methods or numerical solution algorithms are introduced in the literature. One of the methods recommended in the literature is the use of modified maximum likelihood estimation technique, which has an advantage of having explicit solutions, so they can yield analytical solution to the likelihood equations. It has so good statistical properties like maximum likelihood estimators. They are explicit functions of sample observations. They are considerably more efficient than the least square estimators for all sample sizes, especially for large N. And they are asymptotically fully efficient under very general regularity conditions and almost fully efficient for small samples. And they are robust to plausible deviations from the assumed distribution and the mild data anomalies. However, this method assumes that the distribution is so specific. That means the shape parameter is known. However, this is not a realistic assumption for machine learning applications. Therefore, we need to extend this methodology for the distribution families for the unknown shape parameter case. So this is the aim of the study, actually. In recent years, this problem is solved via adaptive modified maximum likelihood estimation method, which combines the modified maximum likelihood estimation technique with the Huber estimation method. In 2009, Tiku and Sürücü recommended these estimators applied to the estimation of location and scale parameters of long-tail symmetric distributions and named them as MML30. Then later on, 1 year later, Dönmez adapted this procedure to linear regression and experimental design analysis, again for the long-tail symmetric distributions and generalized logistic distributions, and named them as revised modified maximum likelihood estimator. Then finally in 2018, Akkaya and Bayrak, me and my colleague, adopted this method to autoregressive models, time series models, again under the assumption of long-tail symmetric innovations, and named them as adaptive modified maximum likelihood estimation method in the memory of Motilal Tuku, who actually initiated the idea and taught this name. So the aim of today's study is to adapt this procedure for the second-order multi-factor polynomial regression estimation, where the innovations belong to the long-tail symmetric family with unknown shape parameter. Then we will discuss their performance in terms of efficiency and robustness and compare these new estimators' performances with the least squares and the modified maximum likelihood estimators. We used reparameterized model for the second order polynomial regression model, where we have second order powers and cross products of the explanatory variables, and each explanatory variable is standardized. And we assume that the disturbance terms AIJs comes from the long tail symmetric family, but we don't know the exact shape parameter, we don't know exact distribution. And when the coefficients of the cross terms and the powers are equal to 0, this model reduces to the simple linear regression, multiple linear regression case. Well, we can show this model in matrix notation as usual, as y is equal to u times the theta parameter vector plus the error term, so that the least squares estimators are directly known as u prime u inverse times u prime y, and we can calculate, we can estimate the standard deviation by the sum of the square of the residuals divided by the number of observations minus the number. If the estimators are not efficient, modified maximum likelihood estimators are introduced in such cases. We obtain the likelihood function, which involves nonlinear function as given zi divided by 1 plus 1 over k times zi squared, where zi is the residuals divided by the sigma. So since they have the likelihood equations involve these nonlinear functions, we cannot obtain the analytical solution for the maximum likelihood estimation technique. So we need numerical solutions, algorithms like ECM algorithms and Newton-Raphson algorithms and so on. But these are all problematic, especially if the data has outliers in it. So if we look at the steps of the modified maximum likelihood estimators, we first write the likelihood equations in terms of the order statistics by the use of concomitants, so that the original pairing is not lost. Then we linearize these nonlinear terms by the first two terms of the Taylor series expansion around the population quantiles Ti values, and obtain these alpha I and beta I coefficients, actually which guarantees the robustness of the estimators. And we can estimate, we can obtain the Ti values from the quantiles of the distribution, so that this method assumes that the shape parameter is known. If it is unknown, we cannot obtain Ti values from these population quantiles. And then finally, we insert these linearized forms of Gi function into the likelihood equations and solve to obtain the estimators, which are given as follows. These are called modified maximum likelihood estimators. They are the explicit functions of the sample observations. Now, what we will do is, as I said, modified maximum likelihood estimators assumes the shape parameter P is known, so that we directly calculate alpha I and beta I from the population quantiles. However, in machine learning, this P is unknown. So that means we have to estimate these alpha I and beta I values from the sample. So for this purpose, we implement the Huber estimation technique. So we first, as we look at the steps of this procedure, first, we have to obtain the initial estimates of the regression parameters. For this purpose, we initially assume that all regression parameters are equal so that the model reduces to a simple linear regression where the explanatory variable denoted by Vi is equal to the sum of the Ui values, square of Ui values, and the sum of the cross values. Then we estimate the population quantiles from the sample by the use of Huber estimation technique, which is equal to the Y values minus T0, which is the initial estimate of the intercept term, minus the T1 times Vi, where T1 is the initial estimate of the regression parameter slope, divided by S0, which is the initial estimate of the sigma. So as in Huber estimation technique, T1 is just a median of the R values given as the difference between my values divided by the difference of the explanatory variables. And T1 is the, T0 is the median of Yi minus T1 times the explanatory variables. And S0 is the usual 1.483 times median of the absolute differences of Yi minus T1 minus Yi minus T0. That means the residuals. Then by the use of these initial Ti values estimated from the sample, we estimate alpha I and beta I coefficients. However, we do some revision in the beta I coefficients to obtain bounded influence functions. So we revise alpha i's as 1 over k times Ti divided by 1 plus 1 over k Ti squared type of thing, so that the function becomes bounded. Then by the use of these alpha I and beta I coefficients, estimates actually, we obtain the initial estimates from the MML estimator equations. Then we have to relax the initial assumption that all the parameters are equal. So we make an iteration and relax this assumption, then revise our Ti values as the residuals obtained by the use of these estimators divided by the estimate of the sigma value. And then by the use of these Ti values, we again calculate alpha and beta I coefficients and obtain the estimators, AMMLE estimators with these new alpha and beta I coefficients. And finally, we make this iteration one more time to eliminate the effect of the initial estimators, so that we obtain the estimates, the new AMML estimates. Well, in these equations, of course, here, as you can see, we have to determine the value for k. We take it as 30 as suggested by Tycho and Sürücü. If k is chosen very large, then weights reduce to 1, so their robustness decreases. And if it is chosen to be small, then their efficiency decreases. Therefore, 30 is a good approximation for this k value. Then to see their efficiency and robustness properties and compare them with least squares and modified maximum likelihood estimators, we run a simulation analysis. We used two explanatory variables for this case and generate these explanatory variables from uniform distribution. And without loss of generality, we have taken the regression coefficients as 0, 1.5, 1, 0.8, 0.9, and 0.5 respectively, and we taken sigma to be 1. We considered that the underlying distribution is long-tail symmetric with shape parameter 16.5 for illustration purposes. So when we run the efficiency analysis, we have observed that all estimators are unbiased estimators for the regression coefficients, and AMML, the new estimators, are more efficient than the least squares for small sample sizes. But as the sample size increases, least square is more effective, so the two methods become competing. Again, AMML and MML performs in a similar manner. However, AMML method slightly underestimates sigma and is more efficient than others for small sample sizes, whereas it worsens as the sample size increases. Then for robustness analysis, we considered
just one request, if you can please speed up things a little bit because we are close to the closure of the session.
13, including, sorry?
If you can speed things up a little bit because we have another presentation, we are close to the
okay.
end of the session.
We are coming to the end, that's sure. We have tried specification distributions coming from different long-tail symmetric distributions, standard, normal, Cauchy, and / extreme distributions. Then we considered outlier models from both long-tail symmetric and normal distributions. Then considered again for long-tail and normal distributions mixture models and the contamination models. Well, in misspecification cases, we again see that it's unbiased except sigma, and AMML estimators become more robust relative to others as the distribution deviates from normality as more. And as the sample size increases, least squares estimators lose this relative robustness compared to AMML more as the sample size increases. Exceptions again in the sigma. And we observe that AMML is more robust than the MML except for sigma. And when we consider the normal distribution, as expected, they compete with each other. Well, when we consider the extreme cases, Cauchy and / distributions, we see that the LS and MML estimators have unacceptably large variances. So the only estimation technique that can be recommended is the AMML, this new method, which is still robust under such extreme cases. And when we consider the outlier models, then again, we see that AMML is more robust than the others, except the estimation of sigma. And when we see the mixture models, again, we see that AMML is more robust. And when we consider the contamination models, again, we obtain the similar results with the other estimators, so they are competing with each other. So to sum up, we can say that AMMLE estimators are as efficient as the modified maximum likelihood estimators and more efficient than the least square estimators, especially for small samples. Besides, AMML estimators are more robust than the others. However, only exception occurs in the estimation of sigma. So that means there's an open door to improve this method in that sense, which is a future work. And we can say that AMML is a promising method for both parametric analysis and machine learning analysis. So thanks for listening. Here are my references.